students, in this video we need to talk about energy diagrams and the energy that goes into and comes out of reactions. So if we take a look at this first slide right here, we can see that it tells us that when we have a reaction, we have molecules that are going to come together, and we're going to need to break bonds and we're going to need to make bonds. Now, whenever we break bonds, this costs us energy, and the picture here tells us that if we have chlorine molecules, breaking that single bond for a mole of chlorine molecule, Cl2, is going to cost us 58 kilocalories. So 58 kilocalories of energy needs to be put into the system per mole of Cl2 in order to break all of those single bonds in all of those Cl2 molecules. Now, if we have regular old chlorines that have 7 valence electrons and they come together to share 2 electrons and form a covalent bond, what happens is we get 58 kilocalories of energy released per every mole of chlorines that form a Cl2. So 58 kilocalories of energy released here, so it's going out. And when we break the bonds, we have 58 kilocalories per mole that has to be added into the system. So how do we quantify this? How do we put this into numbers so we can put it on a chart for ourselves and we can easily see how much it costs us to break different bonds and how much energy is released when we make certain bonds? Well, we call this whole concept delta H. So this is the heat of reaction. It's also called the enthalpy change. Enthalpy is just a fancy word for heat. Okay, so the delta heat, or the heat of reaction, is the net energy that's absorbed or released when we have a reaction. So if we do a reaction and we break bonds and we make bonds, and we have to have a net input of energy, so the reaction has to suck in energy from the surroundings, delta H is positive. So that would mean that delta H was greater than 0. And we see our old friends, the words endothermic and exothermic here. So we've heard these before. So when delta H is greater than 1, this is an endothermic reaction. When delta H is less than, I think I said 1, I meant 0. So when delta H is negative, we're going to have an exothermic reaction. That means we have a net release of energy. So if we look at the bond right here, chlorine to chlorine, in order to break that bond, so in order to cleave that bond, we've got to put in 58 kilocalories per mole of energy, and we say that that's a plus 58 because we need the delta H to be greater than 0 there. And if we make that bond, so if we have 2 Cl's that are floating around both wanting to have an octet, and they find each other and they both say, woo, let's go ahead and share electrons so we can both pretend we have an octet, and that bond forms, 58 kilocalories of energy comes out. So we call that negative 58, and that's per mole of chlorines that make that bond. And this is exothermic, meaning the energy is released, the energy goes out. So this negative right here means out. The heat is going out from whatever's happening here. So just to look at a different reaction. So instead of chlorines, here we have the hydrogen molecule. So we've got H2. So if we break that single bond right there, that's going to cost us 104 kilocalories per mole of H2s that we do that to. So that plus right there, it means input energy. You got to put energy in to break that bond. And then we will get a couple of individual hydrogen atoms. Now, when we make the hydrogen molecule, so we take two individual hydrogen atoms and we bring them together to make that bond, there's going to be a release of energy, because when we make bonds, we release energy. And it's exactly the same number as when we broke the bond, except it's a release of energy. And again, you guys, we indicate that with the negative symbol. Okay, so what happens when we have a diatomic molecule, so meaning two atoms make up the molecule, and the atoms are different? So we have an H and we have a Cl. Well, the same thing happens. If you want to make the bond, you're going to release energy, which is what's happening here. If you wanted to break this bond, the delta H would be what to break that bond? Well, breaking bonds means our delta H has to be positive, because we have to put energy into breaking something. Just like if you guys were going to break a ruler or something like that, you'd have to put energy into doing that. And that's exactly the opposite of this up here. It would be positive 103 kilocalories per mole of HCl that we wanted to break. Okay? Now, the stronger the bond, the higher the bond dissociation energy. And dissociating it just means you're breaking it apart. So the stronger something is, the more energy you have to put into break it, which should make sense to us. And when you form a really strong bond, you're going to get a nice release of energy. Now, when we go down a group on the periodic table, so say we go from fluorine to chlorine to bromine to iodine. So if we were to look at a periodic table and we looked at the halogens, we'd see that we had fluorine, then chlorine, then bromine, then iodine. What tends to happen is it takes less and less energy in order to break that single bond, which is a little bit interesting. But what happens is, as that anion, as the fluoride or the chloride or the bromide or the iodide get larger and larger, the valence electrons on the very outside of the electron cloud, those are held less tightly because they're farther and farther from the nucleus, because the atom's getting bigger and bigger. So it holds on to that electron. It has a weaker hold on the electron when it's bigger. So iodine is a lot bigger than fluorine. So the electron that's on the outer shell right there, on the outer of the electron cloud right there, isn't held as strongly, which means that it'll go ahead and let it go when it's in a bond with somebody else. So say we have this right here, and those two electrons are in between the hydrogen and the iodine. The iodine's like, all right, we can break that bond. I don't really need that electron. I got enough electrons. And so it costs less energy than it would with a smaller atom like fluorine. So this brings us to, how do we represent this on a graph? Well, exothermic reactions, what you guys will see is that the reactants are here, like they will be with the endothermic reactions. And then you have an input of energy that you have to have in order to make the reaction go. And we know this is our energy of activation. But just so we can make it clear again, to get from down here to up here, we have to put energy into the system because we're breaking bonds there. Now it's going to get to the transition state. And the transition state, That's that very moment in time where you have both bonds being made and bonds being formed. I think I just said bonds being made and bonds being formed. Bonds being broken and bonds being formed. So when we get to the transition state, after the transition state, what we have is the making of bonds, and that's going to release energy. And when we release energy, remember, you guys, we put the negative symbol there. So if we added the plus E with the negative E together, what we would find is we have a net release of energy. And the net release of energy is right here. And that's our delta H. So the delta H for an exothermic reaction is less than 0 because the negative E right here, the energy released, was a whole lot greater than the energy taken in, which was the positive value. And when your negative value is really large and you add it to a smaller positive value, your net value is going to be negative. So that's the energy value, that's the energy diagram for an exothermic reaction. And of course, your products are down there. Now for an endothermic reaction, what we have is we have our reactants down here, and we need to put in a lot of energy to get up to the transition state, okay? And that amount of energy is equal to the energy of activation, and then you hit the transition state, and what you have is a little bit of a release of energy because you're making bonds, but you can see that you don't release as much energy as you had to put into this system to make the reaction happen. So the delta H is positive because the delta H is the difference between this guy and this guy right here. So the delta H is a positive value because that one is bigger than that one. And if you add a very large positive value to a small negative value, you'll have a net positive value. So we have that delta H is greater than 0 here, okay? Now back to this slide right here where we had just done exothermic reactions. What we have is a reaction of methane, CH4, with a couple of oxygens. And methane, if we draw out the Lewis structure for that, looks like this. And then we're adding it to a couple of oxygens, and O2s have a double bond between them. And what we're making is carbon dioxide and a couple of waters. So we have to break 4 carbon-hydrogen bonds from the methane, and we have to break 2 oxygen-oxygen double bonds. Now, I'm not going to give you guys a chart and provide you with all the values and have you add those up. That is something that you'll do in 1A if you go on to 1A. But just know that we have to break those bonds. And then what we have to do is we have to make a couple of carbon-oxygen double bonds, and we have to make 4 hydrogen-oxygen single bonds. Now, the amount of energy that is released when you make those 6 bonds exceeds the amount of energy that you need to put into the system to break those 6 bonds right there. And the difference is a negative 213 kilocalories per mole. So we're going to release 213 kilocalories. And remember, kilocalories, that's a unit of energy like joules or kilojoules, or small c calories, and kilocalorie is equal to a big C calorie, which again is equal to 1,000 small c calories. So we're going to release that energy when we do this reaction. For our endothermic reactions, what we're going to do is we're going to have to add heat. There's a net input of heat into the reaction in order for it to happen. And an example of this for you guys is the making of glucose. So what we have is we have 6 CO2 molecules. So we have 12 carbon-oxygen double bonds to break. And we have 6 oxygen molecules. So we've got 12 hydrogen oxygen single bonds to break. And what we're going to make is 6 oxygen molecules. So we make 6 oxygen-oxygen double bonds. And then we're going to make a glucose. And a glucose is a ring of carbons, and we've got 1 oxygen in the ring, and it's kind of got a weird shape, and it's got a lot of hydrogens and oxygens on it. Now those hydrogens, or that hydrogen and that OH that I drew right there, those are above the ring, okay? So imagine the ring being flat and that OH and that H are above the ring, and this H and this OH are below the ring. So that hydrogen that looks like it's inside of the ring, it's not inside, it's going up. So it's just kind of hard to draw something in 3D that's on a piece of paper that's 2D. And then we have a hydrogen coming off the bottom of that carbon right there that's below the ring. Okay, so breaking all of these bonds right here, it's gonna take up a lot of energy. And then we're going to make all of these bonds over here. And when we make those bonds, we're going to release energy, but we're not going to release as much as what we had to put into the system to break all of these bonds right here. So we have a net input of energy of 678 kilocalories per mole of our glucose that we're going to make. So we've got more energy going into the system than coming out, and so it looks like that. Lots of energy in, just a little bit out, and a positive delta H, which we see right there. Okay, so what happens when we add a catalyst into the equation? So first, here's a little chart showing you everything that I just told you, but in a chart form. So when we add a catalyst into the system, the catalyst is going to give the reaction a different pathway to take in order to get from reactants to products. And the pathway that it can take is going to have a lower activation energy. So you've got to put less energy into your system in order to get the reaction to go. So the catalyzed reaction happens faster, the uncatalyzed reaction is slower. Sometimes it's so slow that we pretty much say it never happens. Now the weird thing about this is this line right here. This is the delta H is the same for both reactions. So if you look at the uncatalyzed reaction, what you have is you have a large input of energy, and then you release energy once you make the bonds. And the uncatalyzed reaction, you have an input of energy, the energy of activation for the catalyzed reaction, but you don't have as much of an input of energy as with the uncatalyzed reaction. And you do get a release of energy, but you have a release of less energy to get to your products from your catalyzed transition state. So what happens is the difference between input and output of energy is the same, because with the uncatalyzed reaction, you have a bigger input of energy, but you also have a bigger output of energy when you make the bonds. With a catalyzed reaction, you have a smaller input of energy to break the bonds, but you also have a smaller output of energy when you make the bonds. So delta H is the same, okay? But delta H being the same does not mean that you get to the products at the same rate. We use catalysts because the catalysts allow us to get to the product faster. So one of the things we're talking about is thermodynamics, and the other thing we're talking about is kinetics there, okay? And thermodynamics versus kinetics, if you go on to take chemistry 1A, you guys will see that again, and you'll do a lot of math on that. If you're not going on to 1A, woohoo, no math. Okay, so looking at an equation or a reaction that uses a catalyst in real life. Well, there is this molecule called ethylene. It's also called ethene. And we've got a double bond. And what we can do is we can remove the double bond and we can add a hydrogen to each of those carbons in order to make the molecule ethane. And ethane still has 2 carbons, but instead of having 2 hydrogens on each of the carbons, your ethane has 3 hydrogens. And where did those hydrogens come from? They came from H2 right there. So you've got to have hydrogen gas. But this reaction won't go on its own. You have to throw a metal catalyst in there. Now the metal catalyst that the picture shows you guys is palladium, but you can also use platinum, and you can also use rhodium, and there's a few other metals that'll work too. But platinum and palladium tend to be the ones that we see for this reaction. So the palladium lowers energy of activation enough that you get a lot of product here. One that we use in real life is a catalytic converter, a catalyst that we use in real life. And what this does is it uses a metal just like the reaction before, platinum, palladium, or rhodium, and it turns some of the gases like carbon monoxide and nitrogen monoxide that are particularly toxic or damaging into other molecules that are less toxic or damaging. So carbon monoxide, if we inhale that, it hops onto our hemoglobin, and it has a higher affinity for our hemoglobin than oxygen does. So that's not really good for our circulation. And what we do is we use a catalytic converter, so it's catalyzing the reaction of those molecules into carbon dioxide, nitrogen, and oxygen. Now this is better for the environment, but it's still not good because carbon dioxide is a greenhouse gas. So we're still pumping out greenhouse gases here, which isn't good for us, but at least we're not pumping out carbon monoxide too. So that is the supplemental video that shows you guys the energy diagrams that will be on the exam. If you have any questions, let me know, and if not, I will see you in the next video. Bye-bye.